All right, so we'll start out with the kind of vector addition you've already done in Science 10, and that's the addition of what we call collinear vectors. Okay, collinear vectors are vectors that are on the same line, or they're in the same dimension. Okay, like up and down, or left and right. Okay, or forward and backward, whatever. Okay, essentially they're one-dimensional. Everybody follow me on those. Okay, so essentially everything is positive and negative. Those are pretty easy. Okay, we're also going to look at, perpendicular vectors. So if something went north and then turned west, all right, being able to find their total displacement would mean here was their initial position, here was their final position. This line would represent their total displacement. Okay, so we would have to calculate that, but that's okay because we would know we would know y and x, and we'd be able to calculate the direction because we could be doing some trigonometry. And we have the opposite side, the adjacent side. We can use Pythagorean theorem to get the hypotenuse, all of that kind of stuff. Okay, nothing you haven't done before, okay, but it is going to involve a little bit of trick. Okay, so like I said, collinear vectors are vectors that are in a straight line. So I went 20 meters to the right, and then I came back, let's say 5 meters left. All right, my total displacement would then be that distance. All right, they're collinear, so they're on the same line. Okay, all types of vectors are added by placing them tail to head. I've done that in all the diagrams I've drawn here. In this first diagram, I drew the north line, and then I drew the west line on top of it. So I put the tail of the second vector on the head of the first. Okay, we always draw them like that because it's kind of like tracing the person's path or the object's path. Okay, it went this, and then it did this, and then it did that, and we just keep drawing the arrows on the end of the last one, so we're following the trail. Okay, same with this one. I first drew my line to the right, and then put the line to the left, put its tail on the head of the first. Okay, we always draw our vectors in that way, tail to head. Okay, we don't want to draw vectors like this, and I see people do this all the time. The question would say, person went 5 meters north and then went 6 meters east. What does that diagram say the person did? It says they ripped in half and went in 2 different directions at the same time. Not possible. Okay, we just can't do that. Okay, that's literally what this is saying. It's saying you went in 2 different directions at exactly the same moment. Okay, that's not the same thing as saying they went north and then went east. Okay, this one's possible, this one's not. All right, it's like the scarecrow, okay, in the Wizard of Oz. Right, some people like to go that way, some people like to go that way, and some like to go both ways. You can't go both ways. Okay? You can only go one way at a time. All right. Right. So all vector quantities, guys, are added the same way. And we're going to deal with lots of different vector quantities. Obviously, displacement's the one we'll probably deal with most often. But you can do this with velocity. You can do it with acceleration, force. Okay, all of those things are vector quantities. And we will be using vector addition in the same way with all of them. The only thing that changes at the end is whether it's in meters, meters per second squared, or newtons. Okay, but the fundamentals of adding them together is the same regardless of what vector quantity it is. All right, so from Science 10, a vector quantity is a quantity that deals with both magnitude and direction. So because direction is an important characteristic, okay, we use arrows to show vector quantities visually. Okay, and the convention is this. Whatever direction the arrow is pointing is the direction the object is going. Pretty straightforward. Okay, the other convention is the length of the arrow represents the magnitude of the vector. So if I've got a vector that is 5 meters east, okay, I might draw it like this. And then I would draw a vector that's 10 meters east, like that. They both point the same direction, but my 10-meter east vector is twice as long as my 5-meter long one. Right? Are we drawing this to scale every single time? No. Okay, it takes way too long if we're measuring every single vector we draw and using a protractor to, get the right angle and all that. Just like approximate scale. Right? If it says 30 degrees east of or north of east, that's like this. Don't draw 30 degrees like this. That's not 30 degrees. Okay, everybody kind of follow? As long as it's approximate, your diagrams will work. Okay, so yeah, that's what this does here. So the direction of the arrow gives the direction of the vector. Okay, and then on the next page here is where the length of the arrow is proportional to the magnitude of the vector. So the longer the arrow, the bigger the magnitude of that vector is. All right, everybody okay with that? All right, very often we're going to be using compass directions. Okay, so north, east, south, and west. So make sure, guys, that you understand that a compass works like this. Never eat soggy wieners clockwise around. Okay, make sure you do it right, because I have people who mess this up somehow, and then their directions are always wrong on their answer. Okay. All right, so lots of times we have to add one vector to another, and that's what we're going to be working on for like the next 2 weeks probably. Okay, so we spend quite a bit of time on this. So if we have to do that, then we do what we talked about before, which is we draw the vectors tail to head. So in this example here, we have an object, or a car in this case, that moves 275 meters due east, and then 125 meters also due east after that. Okay, so we've drawn the first vector here. Okay, this is our 275 east vector. And then we have our 125 meter vector on the head of that one. Okay, so we've drawn them tail to head. Now the total displacement of this object would be, add these two together, it's 400 meters east. Everybody okay with that? Okay, so collinear vectors are pretty easy. You've been doing those already. Okay, the big thing here is we always draw them tail to head, whether they're collinear, perpendicular, or neither one. Okay, because we're going to get to questions where I've got this vector and that vector. Okay, they're both angled, and I've got to figure out what the total displacement is. Okay, that's where we're headed to. All right, so the corresponding two displacements are those two lines. That's what we talked about already. This one was 275, and this one was 125. Okay, and we added them together, we got a total of 400 meters east. Okay, we just add them up. Okay, now let's say we got this example. I have the 275 meter east vector, and it's okay in there. Then I've got 125 meters north. All right, so I still draw them tail to head. Okay, so I still put them in that way. But now I've got to figure out what my total displacement is. My total displacement is my change in position. Initial position to final position. And it's always the straight line. Right? So that's this red line here. Now, how am I going to figure out how long that line is? Right, use the Greek geek. Okay, Pythagoras is the Greek geek, by the way. Okay, guy studied triangles his whole life. Right, so he discovered that whole a squared plus b squared equals c squared thing. So I'm going to use Pythagorean theorem to calculate the hypotenuse of this triangle, which happens to be the magnitude of my displacement. All right, so I'm going to find my total displacement to be 125 squared plus 275 squared. Okay, so my total displacement is 302 meters. Okay, that's only the magnitude of my displacement. Now I need to know what direction that's going. So I need to find what theta is. I know all three sides of the triangle now. I can use any one of the trig functions, sine, cos, or tan, to find this angle. But here's my caution on that. If I make a mistake in calculating the hypotenuse's size, and then I use it in another calculation, will that one be right? So I generally use the sides I'm given, just in case that happened. All right, so I'm going to go with 125 and 275. So what trig function am I going to use if I'm going to use those two sides and I'm looking for this angle here? No, cos and sine both require the use of the hypotenuse. And I've don't want to use the hypotenuse because that's the one I calculated. So if I want to use this one, which is opposite, and this one, which is adjacent, I want to use tan. Okay, I could use cosine because I do know what this one is. Okay, then I would use the 275 and the 302. Right, but in general, we try and use the ones that were given, not the ones we calculated. All right, so theta then is going to equal the tan, or tan to the minus 1 actually, of 125, which was the opposite side, over 275. Okay, just so you know where I got that from. Tan of theta equals opposite over adjacent, and I just manipulated for theta. So I brought tan over here, which means I inverse tan. Okay. All right, so inverse tan of 125 divided by 275. So the angle's 24.4 degrees. All right. The two numbers I was given in the question both have 3 significant figures. So my answer, including the angle, should have 3 significant figures. So my final answer is that the total displacement is 302 meters at 24.4 degrees. Which direction? North of east. Okay, and I have to say it that way. Okay, I have to say north of east. I can't say northeast. Why can't I say northeast? Right. It doesn't tell me whether it's, so here's my compass. Okay. It doesn't tell me whether it's this one, which is north of east, or this one, which is east of north. They would both be 24 degrees. Okay. But they're obviously not the same direction. Okay. This one is north of east. Okay, everybody follow me? In other words, it was measured from east, and it went 24 degrees in a northerly direction from there. All right. The best way probably initially to figure that out is to kind of draw it out. Some people kind of use their hands, so like, okay, I'm going east, and then I'm going this way. That's north of east. I actually see people do that on the final exam sometimes. They try and hide it, so no one will see. No one's looking anyway. I don't know why they get all worried about it, but okay, whatever you need to do in order to figure out which direction that is. I often draw the compass rose and just kind of go with it from there. Okay, but that's going to be 24 degrees north of east. All right, questions on how the perpendicular one works? Okay, this should be relatively straightforward, right? We've done with right angle triangles for years in math and stuff. So, okay, so this is what we just did, the math of what we just did. All right, so we're going to do a couple of examples here just to make sure we know what we're doing. All right, write this one down, give it a try. It's pretty easy, it's just collinear stuff. Okay, so when they say figure this out graphically, they mean by like drawing a picture, like a graphic, not using a graph, okay, just so you don't get confused. All right, so on this one here, in this town where there's obviously nothing to do, these people have this race where they move 10 meters forward and untie a series of knots. Okay, and then they move 5 meters forward and solve a puzzle. And finally, they move 25 meters forward to the finish line, where I don't know what they do after that. Make snow angels or something, I don't know. Okay, all right, so there's my vectors. I've drawn them tail to head, okay, and now I can just add them up because they're all in the same direction. Okay, they're all forward. Okay, so we're going to have a total displacement here of 40 meters forward. Okay, everybody all right with that? I think that's about as easy as they could possibly get in terms of vector addition. All right. I want you guys to write this one down and give it a try. This one's going to have some perpendicular stuff as well as some kind of collinear stuff. So I'm going to give you a few minutes on it. All right, so our first step in solving this question is to draw the picture. Okay, so it says that they left their tent to go to the lake. They walked 0.8 kilometers south. Okay, then they walked 1.2 kilometers east. Okay, so I'm drawing them tail to head. and approximately to scale. Okay? And then they walked 0.3 kilometers north. Okay? So that's the path that they followed. That means their overall displacement then is represented by this line that goes from their initial position to their final position. Everybody okay with that? All right. If I'm going to figure out how big that line is, I should probably make it part of a right angle triangle. If I can find the two sides of that right angle triangle, I should be able to figure out the direction as well as the magnitude of the displacement vector, the green line. Right? So how big is the horizontal or x component of that triangle? 1.2 kilometers, right? This is a rectangle now, so this is 1.2 kilometers. Okay, they went 0.8 kilometers south and then came back 0.3 kilometers north. So how big is the y component of this, or the vertical side? Half a kilometer. Okay, because they went 0.8 down and 0.3 back up. Everybody follow what I did there? Okay, this is kind of our next step, is finding what we call the vector components. That is the x component, or the horizontal part, and the y component, or the vertical part of every question. We can turn any vector we want into a right angle triangle, as long as we kind of draw the right lines. Okay, so now I've figured out the two sides of this triangle. I should be able to figure out what their displacement is in terms of magnitude, as well as the direction. Okay, I could have also drawn the triangle this way. All right, that would be fine. I'm going to get the same displacement, but I'll get a different angle. Is that okay? Yeah, it'll be the complementary angle to this one. They'll still be the same direction. Okay, one will just be east of south, and the other will be south of east. Okay, almost every vector addition question has two correct vectors if it's a compass thing. Okay. All right, so I'm going to find first off the magnitude of the displacement, and to do that, I'm going to use Pythagorean theorem. So that's going to be 1.2 squared plus 0.5 squared, square rooted. So my overall displacement is 1.3 kilometers. Or at least the magnitude of it is. Now I've got to find out what the direction is. Since I originally drew the triangle this way, I'm going to find this theta right here. All right, so that's going to mean the 0.5 is my opposite side, the 1.2 is my adjacent side, and I'm going to use tan. Okay, so the tan of theta equals the opposite side over the adjacent side. So theta will be the inverse tan of 0.5, the opposite side, divided by 1.2, the adjacent side. Whoa. All right, so my angle ends up being 22.6, but I think I only have two significant figures, so it's 23 degrees. All right, so that means then my final answer for this question, which has only two significant figures. Why does that number only have two significant figures and this number only have two significant figures? Yeah, you don't count leading zeros, okay? Leading zeros are not significant figures, okay? They're not a measured value. You can't measure nothing, and there's nothing at that position, all right? Everybody follow? Trailing zeros, on the other hand, this zero is significant. I wouldn't have written a zero here unless I was sure it was actually a zero, okay? I would have written like 1 or whatever, okay, if it was anything other than that. If it's blank, then I didn't measure anything at that position. Right? But if I put a zero there, it's because I'm sure it's a zero. All right, so now I'm going to put in my final answer here, which will be 1.3 kilometers at 23 degrees south of east, which means I could also write that it was 67 degrees east of south. Okay. It would depend on which way I drew the triangle. Questions on how I did that one? Yeah, we've already done that. Okay, we're going to leave it at that. Hey, everybody, okay with the perpendicular and collinear ones? Okay, we're going to talk about the next kind then here, just a